video. Righty, I'm going to hand over to Quinton now.
Okay. Hi, everyone. My name is Chegofatso Quinton Bapela. So today I'll be sharing with you about blasting geological consideration in designing a bench blast. The presentation will follow this layout. Sorry about that. Okay. So the presentation will follow this content layout, starting off with an introduction, which will basically be in the sense of mining, then defining a blast and its significance. And then we will go on to talk about controllable factors when we design a blast. And then we will go on to talk about the uncontrollable factors, which is basically the geology of the whole blasting. And then end off with a small conclusion based on everything that we will have discussed. So basically, in a mining sense, a bench refers to a horizontal or a gently sloping platform created during open pit mining or quarrying operations, and they are used to provide access, allowing mining equipment or personal access to the ore. So benches can also be used to control slope stability by creating a series of flat or gently sloping faces. They can also be used to facilitate drilling and blasting operations and result enabling access to the ore. A bench can also be characterized by some of the features seen also on this figure, which is a bench floor, a bench face, right over here, and then you can also have a bench angle. The face angle, which is basically just overall gradient of the bench. You have a bench height, the vertical extent of the bench and the high walls, and then you have like a toe, which is the intersection between the high wall and the bench floor, and then you have the bench width. So this is the horizontal extent of the bench, and then you have a crest, which is basically sort of the end of the far, like here, so it's on the far extent of like the bench floor and the high end of the high wall. So then we'll go on to define blasting. So a blast is a controlled explosion. So with the aims of breaking up rock into smaller fragments. So the blasting operation generally includes drilling holes, placing a charge and a detonator in each hole, and then detonating the charge and clearing away the broken material. So the primary objectives in rock blasting are to optimize blast performance and ensure the safety of everyone by implementing the safe practices in and around the blast site. So the secondary objectives of a blast include maintaining the stability of a high wall. That is done usually by doing a blast called the pre-split, and then fragmenting rock masses to reduce their downstream hauling and crushing costs. I mean, you also want to have rock fragments good enough to be good enough. Tailored for excavation purposes, like specific machines used to excavate. You also want the rock fragments to be in the right amount of size to be passed down to the crushing stages. You also, in blasting, you will also want to consider that you want to have your rock sizes also in a specific size that allows for the efficient transportation without like damaging the loading and haul equipment. So this is a typical design of a bench blast. So a bench blast refers to the planning and calculation of blast parameters for a specific bench in an open pit mine. Some of the key considerations in designing a bench include the bench geometry, which is the height, width, and slope angle, the geology, which is the rock mass, type, hardness, the discontinuities, which is the joints and fractures, and weaknesses. You also consider the explosive types and quantity of the explosives, the drilling pattern, which includes the hole diameter, the depth, spacing, burden, and orientation. You also consider the charging and stemming material, which is used in the holes. You also want to consider the safety and environmental concerns, which include the vibrations, the noise, and the possible fry rocks during the blast. Here we come to the controllable factors which we use when designing a bench blast. So for this presentation, I just limited myself to one key factor, which is called the rock mass rating, and it considers multiple parameters to assess the rock. So a rock mass rating considers the strength of intact rock, which is usually what is used is the uniaxial compressive strength. You consider the rock quality designation. You also consider the discontinuities, and then you also consider the groundwater conditions in the pit. So the rock mass rating goes from 0 to 20, which indicates very poor rock, then 21 to 40, which is attributed to poor rock, 41 to 60, which is considered fair rock, and then 61 to 80 is considered a good rock, and then 81 to 100 is considered very good rock. So here is sort of an illustration of what is used to calculate the uniaxial compressive strength. Generally, harder rocks with uniaxial compressive strength values require more energy to fragment, and this results in larger fragment sizes, fewer fines, which is debatable, but in lower uniaxial compressive strength is usually associated with softer rocks, and rocks which are easier to fragment, resulting in smaller fragmentation sizes, more fines, and easier blasting, which is also debatable in the sense. So as the uniaxial compressive strength increases, the fragmentation size also increases. So for harder rocks, produce larger fragments, making it more challenging to achieve desired fragment sizes, higher energy requirements, and then which also means that fragmenting will require more explosive energy to achieve desired fragmentation. And then the blast design complexity also increases. Harder rocks may require specialized blast designs, such as more holes, smaller burdens, or specific explosive types. Conversely, as uniaxial compressive strength decreases, fragmentation size decreases also. And then this results in softer rocks, which produce smaller fragments, making it easier to achieve desired fragment sizes. And then blast energy requirements also decrease, which means you would require less explosive energy to achieve desired fragmentation. The blast design also becomes simpler because softer rocks often allow for more straightforward blast designs. And the rock quality designation. So this is defined as the percentage of the length of intact rock pieces longer than 10 centimeters obtained from a borehole relative to the total length of the borehole. So the relative quality designation calculation involves measuring the length of the intact core pieces obtained from a borehole and adding the length of all pieces longer than 10 centimeters. So the rock quality designation significantly impacts blasting design in several ways, and these include fragmentation. So RQD affects the ease of fragmentation, with higher RQD values indicating more difficult fragmentation. It also affects the drilling and blasting patterns. So in essence, it affects or influences hole spacing, the burden, and explosive selection. So it also affects the explosives energy requirements. A higher RQD values often require more explosive energy to achieve desired fragmentation. They also affect the blast hole diameter and depth, in the sense that RQD, in the sense that high, so in a sense that you would, so for intact rock, you would probably want to use larger spacing and burden, as the rock wouldn't be in a state that allows for energy to kind of move around the fractures and empty spaces. So RQD also affects the stemming and plugging. It also affects the blast timing and sequences, and it also affects the rock support and stabilization requirements. So in general, as RQD increases, blasting becomes more challenging, more explosive energy is required. So you want to have tighter drilling and blasting patterns, and more specialized blasting techniques may be required. And conversely, as RQD decreases, blasting becomes easier, less explosive energy is required, wider drilling and blasting patterns can be used, and more straightforward blasting techniques can also be applied. So, and then another geological parameter that affects blasting designs would be the discontinuities. So the spacing of discontinuities, such as joints. So as joint surface separation increases, it becomes difficult to get a smooth excavation profile from blasting, as open joints hinder the correct propagation between the perimeter holes. On the other hand, the chance of overbreak reduces if joints are tight and cemented. Joint openings also reflect back the explosive energy, just like a free phase. Thus, no split plane is produced. So discontinuities can also affect blasting design in the sense that, the frequency of discontinuities, if discontinuities are present, then the effective area of influence of a hole reduces, because the gaps of the joints will not only hinder the propagation of the radial cracks, but will also provide easy passage for the gases to escape, thus reducing the borehole pressure. The fragmentation and heave of blasted material will be reduced as a consequence. Just like in this figure, on the far left, this is an idealized crack. So this is usually what is intended when you design a blast. So this, and then the middle figure shows shows a joint system, and on the far end it shows this is the blast fragmentation. It shows that these planes of jointing kind of act as shock absorbers that terminate the energy that is distributed by the explosives, and thus the perimeter in which you would have loved fragmentation to extend becomes limited. And then the other aspect of blasting design would be considering groundwater, in a sense that water significantly influences blast design in several ways. And these include reduced explosive performance. Water absorbs and reduces explosive energy, leading to decreased fragmentation and increased vibration. Water alters the rock properties, in a sense that water changes the rock mechanical properties, such as increased weight, reduced strength, and increased friction. Also, water affects blast design in the sense that it increases drilling difficulties. Water-filled holes can cause drilling problems like deviation, sticking, and increased wear of machinery. Water also affects blast design in the sense of charging and blasting. In a sense that water can affect the loading initiation and propagation of the explosives. It also increases the chance of fly rock and vibration. So water can also change rock fragmentation, in a sense that water can lead to more fine, small particles and less uniform fragmentation. It also has an impact on blast timing and sequences. So this would lead or require you to make some adjustments in the timing and sequencing of your blast. To also address some of the challenges that water can have on a blasting design, you tend to also use like water resistant explosives, increase explosive quantities or energy, adjust drilling and blasting patterns, implement specialized charging and blasting techniques, monitor and control water levels, use numerical modeling and simulation, also consider alternative blasting methods, for example, underwater blasting. And in conclusion, geology is important as a science and field of practice, and plays a significant role in the design of blasting of a blasting. So an understanding of geology also contributes significantly to a safe and accurate and efficient mine production. Therefore, an investment in the practices and understanding of geology is bankable. And come to the end, and this is the end. So some of the sources that I used for this were listed here. Thanks.
Thank you so much. That was incredibly interesting. Are there any questions or comments? I see somebody giving you, oh, Justin applauding there for you, Quinton.
Yeah, Quinton, I do actually have one or two questions, if you don't mind, bud.
Okay.
Thanks for your presentation. With your geology and your RQD and that, do you guys have a live geological model or geotechnical model that you use for your blast design, or is it considered on a blast by blast basis based on sort of whole mass parameters? So you go, well, this rock type has a standard RQD of, or an RMR or whatever it is, of 60. And so we will need to have this powder factor, this level of stemming and things like that. How do you link the geology to the blasting process, I think is the question I'm trying to get to.
We actually have, we do have a geotechnical map that is submitted prior to the block preparation. And then that allows for the blasting engineer to kind of make considerations, especially like, for example, the way that you would blast the rocks maybe that are more on the surface. On the surface, is not the same way that you would want to blast your ore, taking into consideration that the surface rock is weathered and much more friable. So you don't want to have like you wouldn't necessarily have to put a larger spacing embedded compared to when you go and blast an ore which is at an approximate depth where with groundwater levels, where then you would have to kind of use like things like sleeve bags, which are basically containers of your explosives. I'm not sure if that answers you.
It does, yes. Yeah. Thank you.
Yeah. Also, I mean, also to kind of add on that, like for example, when you would also consider the reason why you would also want to be blasting. I mean, if you want to protect a high wall, the type of blasting that you would the blast design for that would be different from a normal blast design, which would be generally for the ore.
Nolene, can I ask a question? Well done, Quinton. We're right, Nolene?
Yeah, go for it.
Okay. Well done. I mean, just a couple of things, observations. You're obviously in a new field, and great that you have made the progress you have. Remember, us geologists, particularly the old ones, are very visual people. You know, we love to see pictures of rocks and structure, and you know, before and after, and maybe I know Nolene probably set you a timeline, so you're under a bit of pressure, which is good. But just you know, a couple of pictures of the geology, the rocks you're dealing with. Are they, you know, flat lying? How do they break? Would be useful. And then I also think, you know, in the early stage of your career, which is where you are, and you've done extremely well to get to where you are and what you're doing, just be mindful of using a crib sheet. You know, you got a little bit flustered and confused sort of in the middle. And not surprisingly, but that's fine. That's all part of why this program's running. And where you were discussing those different types of fractures, even for me as a geologist with lots of experience, but not in blasting, you know, you could have had a little description there of the different types of structures that you were talking to. It would have helped you, and I think it would have also helped the audience. You know, that's just a couple of little suggestions, but I think and I think you know, and you'll find it useful too when you do these presentations, and you're going to, with BMI, I presume, end up doing, you know, other blasting work. I mean, a presentation like this is also a very good record of what you've been doing. You know, just file it away in your memory bank. Because one day, you know, you might want to go back to it, but add a few, you know, nice pictures. And nowadays, there's no real excuse for not taking pictures. We've all got these smartphones, which are perfect for taking a few pictures. And I presume, as the geologist, they should allow you to use it in the pit or wherever you're working. So those are just my comments, but well done.
Yeah, I do take pictures. Even like a couple of moments ago, I was in the field taking pictures. I was just quite unsure about the permissions that you would require from the mine before sharing their details, stuff like that.
Yeah.
So I think that was basically one of my challenges.
Okay, no, that's fine. But you know, I think pictures tell a 1,000 words is, you know, a really important part of a geologist's armory or what he uses along the way.
Thanks, John. So, Quinton, there is another technical question for you in the chat. How often do you consider groundwater dewatering when planning to blast?
I'm not particularly sure about that, but what I have noticed is that there's usually an ongoing dewatering system that is put in the pit that continuously takes out the water. And from my observation, it has continuously runs throughout the day. So I'm not sure if that answers your question, Shuaib.
Yeah, and to be devil's advocate, Quinton, where does that water go? I mean, you'll know you're working in mining in a very we've had a couple of exceptional years of rain, and I think you've had even rain up where you are, but we live in this exceptionally dry country, and the farmers around you are probably already looking at water supplies and I think we as a geologist, and I'm just talking again from an experience point of view, in the past, the perception of us geologists, and Nolene can perhaps add, is that you make holes in the ground and you make a mess and you screw everything up and you walk away, and then someone else has got to deal with the legacy. And I don't think that's how your company works and how you work and how the rest of us work. But I find that a really interesting question, and perhaps you, as a geologist, want to just again, when it comes to water management, it's a hugely important part of mining. It's a hugely important part of our whole environment. But again, it's a sort of thing in developing your career that you probably want to take half an hour, find out from the mine and your management, in a meeting. I mean, you're not going to go and just sort of rush in and say what's going on here, but just as part of the whole learning process. Because invariably, in the world today, environmentalists are going to more and more challenge mining operations and how we manage water and the environment and plant species, etc. Maybe you want to add, Nolene?
No, John, I think you've covered it. Quinton and I chat often. Oh, Justin, if you'd like to ask a question or offer a comment.
No, it's I think John's exactly correct. What we're seeing now is, especially with the UNFC reporting criteria coming into play, the broader considerations beyond just drilling a hole in the ground, so to speak, is becoming far more important. So we, geologists have always been, I think the best way to describe us is a jack of all trades in some respects, because we've got to consider so many different parameters, but that sphere of consideration is growing. I think we're spending a lot more time thinking about the environmental componentry than we have in the past, which is a great challenging space to be in. But again, it's perhaps a distraction sometimes.
Yeah, I think you're absolutely correct, Justin. I mean, we do spend more time thinking about environmental and SEG stuff than when I started, and I'm sure yourself. So not only is it growing, it's also changing a lot. I think as your career progresses, not only are you moving into more senior positions, but the entire mining environment is changing all the time.
Yeah, agreed. Spot on, Nolene and Justin. Good points. And just to add, you mentioned jack of all trades, but geologists, one of the great things about geologists, geology is not an exact science. So, and you're going to cover, like you've done, Quinton, even in this talk. So you've got a geology degree now. You're in blasting, and then you were talking about water. And that's one of the great aspects and attributes about geology. We really cover a lot of bases, and we should look to do that well and be proud of these all these aspects that we do get involved in. And you young people, it's incumbent upon you to improve what. And I say this positively. When we worked for the mining companies, and thinking of myself, and I think Nolene would have had some of that experience. We kind of got put in boxes. We worked for a big company. I don't regret working for De Beers, but we were in a box. I mean, when I joined De Beers, I was exploring for diamonds, but I wasn't allowed to see a diamond. And I lived in Kimberley, and Harry Oppenheimer House was up the road, where De Beers brought all their Southern African diamonds to sort. But we were confined to the boxes. Now that's changed a lot, thankfully. So you guys have to do it differently and better from the way we did it. And I say that all of that positively. But thanks, it was good.
Right. Are there any other questions from other people? Okay.
Yeah, Just one more, sorry,
Go for
Nadine, I
it.
do apologize. Quinton, you sound happy at the job. You enjoying your time there? I think that's the question. Is this providing you the challenges and the diversity of experience that you were hoping for?
Yes, it's challenging and worth it, because you actually get to see the end result of your input more often. Almost every time, a week doesn't usually go past without you seeing the input that you might have had, and that's, I think, one of the most fulfilling things that you can ask for from a job or a career, I think.
That's awesome, bud. That's really good to hear.
Yeah.
That's amazing. Yeah, that direct impact, I think, is one of the things we all crave. So I'm really glad to hear that.
Yeah.
Congratulations. Well done.
Thank you.
Yeah, my experience of Quinton is the bigger the challenge and the higher the tree or the mountain he's got to climb, the better, the more he likes it. So keep it up.
Yeah.
Not so, Quinton.
I want to put someone on the spot. Chico, I think they asked a question. He probably would know about water. Chico.
With you?
Oh, there's someone on the call. Chico.
Yeah, Quinton, what's up?
Where do they put the water from the mine? You probably know.
Well, they dewater and they put it in surface water ponds that are lined. So yeah, that's pretty much where the water goes from the pit into surface water bodies around the mine.
Oh, okay.
Great, thank you.
I did notice the pond. Yeah.
Sorry, Quinton, I was
Yes.
just going to go, wow, look at you already delegating. That's pretty awesome.
No, we went to school together and also worked at SLR. So their division also works with the mine that I'm at now. So that's why I'm like, he might know.
Right, I would like to thank Quinton and everybody on the call for taking time out of your busy schedules to join us and to support our mentee talks. The next one will be on the 7th of August. Keep your eye out. You'll be getting the Monday mailers as well as it's on the website. This recording will be put onto our YouTube channel in the next couple of days. So please feel free to share it with your friends and colleagues. And we'll see you again soon. Thanks, everybody.
Thanks, Nalene, and well done to everyone, Andrew. Good stuff.
Oh, thanks, John.
Have a good one. Enjoy the rest of your holiday.
Thanks. Well done, Quinton.
Thanks.
Cheers all. Have a good one. Thanks, Quinton.
Thanks, Justin.
Thank
Take
you.
care.
Right, all sorted. Okay.